with GADTs, the complexity is exposed in the church encoding. You can see that the actual way of working with a GADT goes through this type parameter R, which is a type constructor itself, which you have to choose. And you're not really free always to choose what that is. As we have seen in the previous tutorial with the higher kind of church encoding, you cannot always choose this type parameter R in a way that fits the type signatures and yet gives you the results that you want. For example, it is not always possible to choose the type parameter R to be a constant functor that just returns the type you want. In other words, it is not always possible to write a function from a GADT to a specific type. The type parameter R must be chosen such that you will be able to supply arguments that are necessary of these types. So, for example, here you need R to be such a type constructor that you are able to provide a function of this type with arbitrary a function with this type, and also a function with this type. So similarly, for our example of the language, R must be such that you are able to provide functions of all these types that are required for GADT to be constructed. In this particular example of the expression language, we chose R to be an identity type constructor, and we were able to compute these things because we knew what this expression language is. It's just a wrapper for some arithmetic. In more complicated cases, this might not be possible, and so we might want to choose R in some other way. And this church encoding, I prefer to view it as exposing the true complexity of the type. And in this particular way, you can make a judgment about using GADT or not in your code. Are you able to manage all this complexity and provide the type parameter R for each use case and provide the arguments for each use case? So this is the way that GADTs are encoded. Let me now turn to existentially quantified types. What are existentially quantified types? It is a type where there is some value constructed, and this value has a type that depends on some type parameter, but this type parameter is not known anymore after the value has been constructed. So outside of the scope of the constructor function, you do not see that type parameter. That is the usage pattern that is denoted by existential quantifier. So here's an example. In Haskell, actually, quite confusingly, you have to write for all in a certain place in order to encode the existential quantifier. For all is the universal quantifier, but Haskell chose this syntax quite confusingly. What this does is that in order to construct a value of type FA, you need to construct this, which requires a pair of functions from bool to t and from t to a, where t is a certain type that you can choose. And you choose it while you're constructing this value. So confusingly, this is called for all, but actually it does not mean that you have to construct this for all t in order to construct a value of this type. It means you can choose t, and for any of that choice, this works. So for example, you could choose t to be Boolean, and then you need to supply a function from bool to bool and a function from bool to a. But if you do that, then you have supplied a value of type fa. The type parameter t is visible only within the scope of the constructor function, but it is not exposed outside, because the type of the resulting value does not contain t. It only contains a, or maybe other type parameters, but not t. In Scala, it's a similar story. You have a trait, but the extends syntax only uses the type parameter a and not t. So you have an extra type parameter t while you're constructing the value of this case class. But once you have constructed it, you don't see what that t was. And that is denoted mathematically in type theory like this. So it's an existential quantifier, and then whatever that is that you are constructing with that, that is the notation for it in type theory. So let me show how this is to be encoded in Dhall. Let's begin with this type expression. Now, if this does not depend on r, then this is equivalent to just fa. So if fa is whatever type expression you want that does not contain r, then you can always write this type and it will be equivalent. Now this is due to the covariant Yoneda identity. So this is always true. Now we usually don't do this because it gives no advantages to write such a complicated type instead of a simpler type. But there is an advantage if you cannot otherwise encode this type in your language. And this is the case now. So we do not have the existential type quantifier as a built-in feature of Dhall. And we are therefore using the church encoding in order to write the Dhall code for it. So how do we do that? Well, suppose that we work with this example where we have this pair of functions, or in the Haskell syntax like this, and in the Scala syntax like this. So this is f of a. This is f of a is a pair of these functions where t is some unknown type. So let's put it in as a Dhall record like this with some chosen type t. Now we have this function from fa to r. Fa is this. So we have a function from this to r, and it needs to produce a result for all types t because it doesn't know what type t was used. And so the function f, which we have to put as an argument here when we use this encoding, this function f will have to work in the same way for all types t. And that means the type of the function f actually has the universal quantifier in t. When we construct the values of this type, we will have a specific t, but the function f needs to be able to accept any t, because it cannot know what t that will be. And so the type of f actually will be this, from an arbitrary type t to this thing to r. And this allows us to write the church encoding. So we have the usual church encoding formula for any type r, and then something to r, but in this case we will have an extra universal quantifier inside, which is not trivial because this universal quantifier applies to this entire type. So it's not really possible to say that this is equivalent to something simpler, via the UNIDA identity. UNIDA identity does not apply here. So this is the church encoding of the universal of the existential quantifier in this example. So let's see how we construct the value of this type. Right, so there's now quite a complicated type. So let's set A to be natural, so then there's going to be F natural. Let's substitute, and then we get this. Okay, so how do we construct the value of this type? We take an arbitrary R as a type parameter. Then we take an arbitrary function of this type as a parameter. We call this function pack, just for convenience. This is going to be the next parameter. And then we're supposed to use this function to return the value of this unknown type R. So we need to apply pack to what? Well, to some type T and to some value of this type. And here we are quite free to choose what T and what value of this type to use. And so this, for example, we can choose T to be integer, and then we'll have some function from bool to integer, and then from integer to natural. Well, we can just write some code of those types. And that's fine. So you see, because the function pack has an arbitrary type parameter T, we are free to choose that type T when we construct a value of the existential type. And that is exactly the same freedom as we want for constructing a value of an existential type. We want the freedom to choose some type as a type parameter inside, which will be hidden, and then some values of according types, so that you get the value of the existential type. That is exactly that freedom that is now expressed quite precisely through a function parameter whose type contains a type quantifier, a universal type quantifier. So now we see that what we need is functions, higher order functions, whose parameters have types involving themselves type parameters. So that, I believe, is called higher rank polymorphism. But this is just the name for it. What it is that it turns out we need parameters of functions, and the types of those parameters themselves must have type parameters. So that is quite complicated, and working with these functions is certainly not very easy. However, this is what it is. This is the difficulty of working with existential types, and this difficulty remains in all languages where you can use existential types. It's just that this difficulty is not in your face. You do not see all these lambdas and all these type signatures staring in your face, but you will still have to write code keeping all this in mind. In Dhall, everything is upfront. You see it right away, what the types must be. Do we have a function of this type or not? It's in your face. So it is not some obscure compiler error that you don't understand, but it is very much in your face. So I found it very, very nice and refreshing to think about existential types as encoded in this way. So it's in some sense, this is the definition of what it means to be an existential type. So let us have a general definition now. Replace this, which was just our example, by an arbitrary type constructor P applied to T. So let's then write the formula. So in this case, it will be like this, but let's just replace that with P and consider P to be arbitrary. And note also, P is neither covariant nor contravariant in T. This is typical. This is okay. Not a problem at all. This is actually typical in situations where you have an existential quantifier. We will never need fmap for p, for example. So then we can write the church encoding in general as a function of p. So this I denote by this exists constructor, which takes an arbitrary p and returns the church encoding of exists p, of the more verbosely exists t pt. And how do you create values of this type? Well, you just do it the same way. You need choose some type, choose some value of type pt, and this is actually this is going to be t and not our type t, but I will fix that. And then apply this sort of construction where we have a function with an arbitrary type parameter and an arbitrary function that itself involves another type parameter. And then we just use that function, apply it with our type t, our choice of t, and our value of that type. So as a reminder, this is a mistake. This must have been our type t in here. So heuristically speaking, the function pack hides the type parameter t inside this construction, and so once you have called this function, the result will be of this type, and you won't know what t was used when constructing it. So this type does not expose t. So that is exactly the freedom and the feature that we want from existential types. So let me show briefly what you do to work with existential types. So you need to create values of those types, and for that we use the function that we call pack also. So it takes an arbitrary p, arbitrary type t, and then a value of type pt, and then it returns you the value of type exists p. So this is a very simple code, which we just generalize from our examples. And then there is a other function, the kind of reverse function, unpack, which takes a value of exists p and returns some other type. But what that type should be is that you should be able to convert arbitrary values of type pt, where t is itself an arbitrary type parameter, to r. So that's what you're supposed to do. How are you going to do it? Well, depends on p, obviously. So for a specific p, you would be able to give functions of this type, which must work for arbitrary t, but not for arbitrary r, and not for arbitrary p. So you would have a very specific r for which you want to extract values of that type from existential type, and very specific p. So for each p and for each r, you would implement this function in a different way, but this function must work in the same way for all t. So that is, for example, how you would do that. It's pretty easy, and it just takes this exists p and applies it to the arguments that you're given. So actually it's nothing more than an identity function on the exists p. So this is an interesting thing, but this is similar to what we had in church encoding before. So the fold in church encoding is essentially an identity function, because the type of the church encoding itself is the fold type. And so similarly here, the unpack is identity function because the type of existential type encoded in Dhall is essentially the same as the type of unpack. So unpack is similar to fold in some sense. And let me then also show something interesting here, which I call the function extension rule. And the rule is that this type from exists P to Q is quite complicated. Is a type that takes as an argument a very complicated expression with type quantifiers and so on. But it turns out that this can be simplified. It can be simplified because if you look at this type exists P to some R, then essentially it's the type that you need to provide as an argument to unpack. It takes an arbitrary t, takes pt, and returns r. So actually it turns out that there is an isomorphism between these types. So this type and this type are isomorphic. The second one is much simpler. It has only one quantifier. This one has lots of quantifiers inside. Well, 2 to be precise. So this is the function extension rule. It's the isomorphism between these types. So a function from an existential type is equivalent to a function with just a normal universally quantified type parameter. So how to prove that these types are isomorphic? I will not go through the proof now. The proof is to show two functions that go from one type to the other and back. So these functions are unpack p and out ep, which are called like this in my text. And then you need to show that the composition of these functions in both directions is identity. Now this is not obvious to show. It requires certain parametricity arguments, and the proof is shown in the appendix of the book. So this shows you how to implement an existential quantifier. I just want to conclude by making a comparison. What is the difference and what are similarities between the existential and the universal quantifiers? Now we can say, well, the existential quantifier is something that is defined like this, and a universal quantifier is something that's defined like this, much simpler, because the universal quantifiers are built in Dhall. But they're similar definitions, so it's some kind of function at type level that takes this, takes p, and returns another type. So takes this kind and returns a type. What are the similarities and the differences between these functions at type level? Well, one similarity is that they are covariant in P. So if you have exists P and exists Q, and if you can map PA to QA for all A, then you can also map exists P to exists Q, and similarly for all, you can map them. But other than that, they're quite different, and so of course the usage of them are quite different. Their type signatures are different. But let me show this covariance. So how does that work? Well, it's kind of a hierarchized map method that you can use. So if you have a function of this type, then you can create functions of this type and also of this type. And you can actually create generic helpers that show you how to do that. So this is the code. So how do they work? Well, they work quite formally. They just substitute arguments in the right way. And this is a little complicated, but essentially, if you look at the type signature of exists, then let's look at this type signature again. So it's a function of p, and then the result has p here in the contravariant position under the parentheses, but the entire parenthesis itself is in a contravariant position. And so this p is in a covariant position in the overall type here. And because of that, you can write an fmap function. Now this is not so easy because there is this extra quantifier here. And here similarly, so this is manifestly in a covariant position. So here, yes, you have here the quantifier, but it's not a big deal. Because it's in a covariant position, you can map exists p to exists q. So given exists p, you apply this exists p with some arguments. So you prepare this pack p, which has the right type for all t, and then pt to r, and that pack p uses pack q, which is given to you, which has this type. So you substitute the type parameter from pack t into pack q, and so on. It's just a bit of substitution, and you're done. And similarly, for map for all, it's just substitution. There's not a lot of calculations going on. It's just substituting lambda arguments so that the types match. And there's only one way of doing it. So this, I just want to conclude with this. This illustrates the power of Dhall as a higher-kinded lambda calculus, where you can express quite complicated constructions quite generically. So it's an arbitrary existential types that are mapped to each other given functions of this type. And again, notice the type of this function has a quantifier, so this is important. This quantifier is inside the parentheses, so it's inside the type of the argument, it's not outside. And so the language, the programming language that supports those features, so this is higher rank type polymorphism, the programming language that supports those features would allow you to encode GADTs, existential types, and all that, even if those features are not built in into that language. That concludes the tutorial.